For this presentation I learned to juggle. At least I tried very hard to. The art of juggling is to get each ball at the right time, at the right place. In this presentation I will tell you about using balls in piston pumps and motors. Well, not these large juggling balls, but these tiny balls. And also here the trick is to get each ball at the right time, at the right place. And this is what we did. Here you see a cylinder block or barrel of an ordinary slipper type pump. Inside we have 9 cylinders in which pistons move up and down. Oil is flowing in and out of these cylinders through the barrel ports. The barrel runs on top of a pour plate or valve plate. Now we have made 3 rather small changes to this design. First of all, we completely removed the silencing grooves from the pour plate. The second change is that we increased the size of the sealing lands. When the barrel port passes a sealing land, there is no connection to either the low or high pressure side of the pump. In the new design, these areas are significantly larger. The third change is not in the pour plate but in the barrel. We made new connections between the cylinders inside the barrel. We call these connections shuttles. Each shuttle consists of a small cylinder in which we put a small ball. Finally, we close the shuttle cylinder by means of a hollow plug. This way, the shuttles will have 2 seats, one at each end of the shuttle cylinder. The shuttle ball can only move back and forth inside its cylinder, and while the ball moves, oil flows in and out of the shuttle. Shuttles act as check valves when the ball is pressed into one of the 2 seats, but the ball also acts as a small piston when it is moving from one seat to the other. In this presentation, I will explain to you how the shuttles work. But first I need to explain you something about commutation. Commutation happens when, in hydrostatic pumps and motors, a cylinder in the barrel switches from one pressure level to the other. It is a short and extremely dynamic process with very rapid pressure changes. In order to explain commutation, we only need to look at a single piston and cylinder, since the same process is repeated in the other cylinders. Oil is supplied to and from the cylinder via the barrel port. The barrel, in which the pistons move, rotates on top of a pour plate. This plate has a high pressure port, a low pressure port and some silencing grooves. Here you see the pump in operation. In this animation we are moving and rotating with the barrel. We therefore see the pour plate rotating underneath the barrel. During each rotation the piston makes a suction stroke and a pumping stroke. The piston has 2 end positions, the top and bottom dead centers, the TDC and BDC. Around these centers, the barrel port switches from one pressure port to the other. This switching process is called commutation. Now let us have a closer look at the commutation, first of all around the bottom dead center or BDC. Here the oil of the cylinder needs to be compressed to the level of the high pressure line. In current pumps and motors, this commutation is realized by short circuiting. A pressure relief groove or silencing groove is used to soften this transition, but in the end high pressure oil just squirts into the cylinder, causing throttle losses, a reduced efficiency, noise and pulsations and cavitation and wear. Half a rotation further on, we arrive in the top dead center, where the oil in the cylinder needs to be expanded. And just like in the bottom dead center, the commutation is also here realized by means of short circuiting. And also here this results in throttle losses, a reduced efficiency, noise and pulsations and cavitation and wear. However, commutation losses can be avoided. Compressing and expanding oil can be lossless, just as compressing and expanding a spring can be lossless. This ideal commutation can be realized by removing the silencing grooves and increasing the sealing lengths. In this example, we will make the sealing lens large enough to get an ideal commutation when the pump is running at its maximum pump pressure, let's say 400 bar. On the left you see what happens when we show the cycle in the PV diagram. The thin grey line is the process with the conventional pour plate. With the new pour plate, both the compression and the expansion are more gradual. However, this design only works in theory, and even then only for one pressure level. If, for instance, we would operate the pump at a lower pressure level, let's say 200 bar, then this pour plate design results in a mismatch. The sealing lens, which were designed for 400 bar, are now much too large and result in strong pressure peaks and cavitation. To avoid these disadvantages, you'll need shuttles. Shuttles are a way to have an ideal commutation in a wide range of operating conditions, independent whether the pump is working at a low or a high pressure level or operated at a low or high rotational speed. Here you see the shuttles represented as hydraulic symbols like double acting check valves. Now there is a tricky part about the shuttle balls. These balls are free bodies, albeit with only 1 degree of freedom to move back and forth between the two seats. But within these constraints, the shuttle ball can be anywhere at any time, which means the ball can also be at the wrong position when the commutation starts. So like with juggling, the trick is to get each ball at the right time, at the right place. We solve this by using pressure differences between the two sides of the shuttles. The shuttle balls are very light and small. Their weight is much less than 1 gram, in this example only 1/10 of a gram. And this makes it very easy to move them by means of a small pressure difference. As an example, a pressure difference of only 0.1 bar is enough to move the ball within 2 milliseconds from one side to the other. Now, we don't want to create a pressure difference, we want to use a pressure difference which already exists in the pump. And the barrel ports create such a pressure difference. The flow through these ports create a pressure differential which we use to position the shuttle balls. The two openings of the shuttle cylinder are connected in such a way that the shuttles kind of measure the pressure difference across the barrel port. Although this is a small pressure difference, it is enough to move and position the shuttle balls. So now we have all the ingredients for an ideal commutation. We have removed the silencing grooves and increased the sealing lens. This allows the oil to be compressed and expanded by the piston movement. We've also introduced shuttles as a means to avoid overcompression and overexpansion. And we have found a way to bring the shuttle balls to the right position before the commutation starts. So let's see how this works and move the middle piston to the bottom dead center. Around this point, the oil in the cylinder needs to be compressed. The shuttle balls have moved to the right position and the shuttles now act as a check valve, blocking the passage from the middle cylinder to its neighbors. Since the cylinder port is closed by the sealing land, the piston movement will gradually compress the oil in the cylinder. Halfway the passage of the sealing land, the pressure in the cylinder has reached the pump pressure of 200 bar. At this point, the green shuttle ball will start to move. Without the shuttles, the pressure in the cylinder would further increase to 400 bar, but the shuttle immediately responds to any overpressure by moving to the other side. Meanwhile, the pressure in the cylinder just remains at 200 bar. And this will continue up to the point where the barrel port opens the connection to the high pressure kidney at precisely the same pressure level. This is an ideal gradual compression which will work at any pressure level. And also at the opposite side, at the top dead center, the shuttles avoid any overexpansion. Also now the shuttle balls are positioned at the right side. Since both shuttles now close the connection, and since the barrel port is closed by the sealing land, the oil in the cylinder will be gradually expanded as a result of the continuing piston movement. Without the shuttles, this 400 bar pour plate design would result in an overexpansion when the pump is operated at a lower pressure. The shuttles prevent this. As soon as the pressure in the cylinder equals the pressure level of the suction line, the green shuttle ball will start to move and supply oil to the commutating cylinder. Due to this extra oil supply from the shuttle, there is no overexpansion or cavitation. And this continues until the port opens to the low pressure kidney of the pore plate. The shuttles create the opportunity for an ideal commutation at any pressure level or operating condition. Shuttles can be applied in any pump or motor which has commutation zones, like in axial piston pumps and motors, but they will also work on radial piston pumps and many other pumps and motors. They can be applied in fixed displacement units, but the advantages will even be larger in variable displacement pumps and motors. We have tested the solution in a wide range of operating conditions up to 5000 RPM and 450 bar. Shuttles increase the overall efficiency. Test results will be presented later, but to give you already an idea, this is what we have measured in our 45cc floating cup pump, an increase of the overall efficiency of up to 3.5%. Especially the torque losses are strongly reduced when shuttles are applied. It shouldn't come as a surprise that the shuttles also reduce the noise level. In our 45cc floating cup pump, we measured reductions of up to 8 dB. Shuttles only require a small change of your current designs. By using shuttles, the pumps and motors will not get any more expensive, but they will have a strongly improved efficiency and reduced noise level. And if you will excuse me now, I have to work and practice my juggling skills.